Okay, so many thanks for taking time at the show to come and listen to this session. My session today, my name is Mike Ferguson, I'm your conference chairman at Big Data London, but my session today is about modern data architecture and how we can build that given all the technologies we have out here, and how does it all come together in an end-to-end architecture that works to deliver value in your organization. So what I want to talk about is what data architecture is and the kind of key elements of that, different example types of that, and ways in which we're seeing that emerge within organizations today. I'll look at the kind of hybrid computing environment that we're trying to implement this on these days, and what's happening there, and the emergence of different kinds of database, which are a key part of data architecture that are out there, and how we're using them, and then look at how they all fit together in an end-to-end offering, and how data should kind of flow, if you like, to try and shorten the time to value and give you a more unified approach towards data delivery. So if I look at just Wikipedia, and you look at what the definition of data architecture is, you can see it covers models, policies, rules, standards to govern the data, how you collect it, how you store it, how you arrange it and integrate it, and put it to use across your organization. Pretty broad definition, covering things like methodologies, database technologies, the processes or pipelines in which you would want to process that data, and any administrative efforts to manage it all across all of that environment. Solution architecture, on the other hand, is kind of restricting data architecture to a specific solution. So, many of you may be solution architects, particularly focused on a particular business problem and trying to look at data architecture in that context. And we've had plenty of examples of that over many, many years. Things like the classic data warehouse architecture, which hasn't changed in a very, very long time. Or another example of that might be streaming architecture, where you've got streaming data coming in on something like Kafka or Kinesis or Google PubSub or something like that, and you've got to filter something out of that. You've got to maybe combine it with other data at rest that could be master data of some kind, perhaps, and then feed that into a trained model in order to drive scores and predictions, or maybe even automate the decisioning, driving alerts or actions, and then maybe filter some of that data off. But you're doing it in real time. You're not even storing it. You're doing it before you store it. And you could be using something like Spark or Flink for that kind of approach. But it's still a very specific architecture for a particular problem. And so it's one example. But I think for most of us, we're building these as silos today. And I think for me, that means we're not running particularly efficiently. We've got, if you look at the green boxes across the bottom, and I look at that and I think, well, how many tools and scripts and code is out there in whatever language across your organization where people are trying to clean and integrate data? And I'm sure it's more than one. It's going to be multiple. And the problem with that is sharing metadata across those tools is nearly impossible. And so the idea to understand what people have invented in any of those silos being shared with what other people are doing in any other silo is almost zero, because they have no ability to know what was being created. And one of my clients said, everybody's blindly integrating data with no attempt to share what they create. I kind of think that's a pretty interesting statement, but obviously the danger is that we end up with these silos and we don't do as an efficient a job as we could. But we're trying to sort of come together to put a data architecture on top of a modern kind of operating environment these days, and that's turning out to be not centralized anymore. We're beyond the data center. We're in multiple clouds. We're in the edge. You may only be in one cloud, but how many of you are now looking at multiple clouds across for your organization today to implement? Okay, quite a lot of you. So we have this challenge of managing data and putting an architecture basically on top of this. And then the question is really, well, how? And how are you going to capture your data, store it, integrate it, and analyze it? Are you at the edge, in multiple clouds, in your data centers, or across all of it? And do you have to keep building these silos for each of these operating environments, or could we come up with a common approach that would pull all this stuff together so that we could manage it across all of this setup? And obviously, when we look at that, we have to think about types of databases. And we've seen an explosion in databases over the last 5, 6, 7 years, or other kinds of data store. If I look at the spectrum, your general purpose, if you like, databases in the middle, your traditional relational databases, which have done a great job as a kind of universal category. But the further you go to either end of the spectrum, whether you go to extreme transaction processing down one end or extreme analytical processing up the other end, you're going to move into specialist databases. And what we're seeing in both sides of that spectrum is NoSQL and relational systems. If you like, new SQL in the area of extreme transaction processing, like VoltDB or NeoDB. NoSQL databases have been around for years, all the way back to IMS, which is still out there, believe it or not, to the Mongos and HBases and Cassandras and so on, Couchbases and whatnot that we see there. On the analytical side, again, you see analytical relational databases, which are widely used around organizations, and several of them here this week. Or you can see other NoSQL analytical systems like graph databases, which obviously don't understand a SQL language. Typically, you've got obviously Hadoop systems, or even Spark being used as an in-memory massively parallel capability to do analytics and machine learning. And I guess if I look at NoSQL databases, there's different categories. And probably for me at least, the main category for analytics is graph. The others are more optimized for what I call operational processing. Maybe you could do some operational analysis on live data, but generally speaking, I think graph databases, are definitely an analytical database. Perhaps for fraud, for something like cybercrime, which are real sweet spots. Also, Hadoop is an analytical system. It's got a file system. It's got multiple execution engines, probably dominated these days by Spark. But of course, Spark doesn't just run on Hadoop. It can run without Hadoop, doesn't need Hadoop. We've got other engines on there as well. MapReduce is kind of pretty obsolete these days. Tez still out there, running on the Cloudera platform now as well. And so we can run some kind of batch processing over there. We can even run some kind of streaming or kind of capability there too with Spark. And Spark has kind of dominated, where you build Python or Java or Scala or R applications, and you send your application into a driver, which will then retrieving your data either from cloud storage or maybe in a Hadoop file system up into memory and do massively parallel compute on it. And obviously I can implement a kind of combination of streaming and batch processing with Spark, and so kind of implement the so-called Lambda architecture in that kind of environment. And then streaming, increasingly popular, whether you're using something like Spark streaming to analyze and process live data. So maybe prepare it and analyze it while it's streaming before you land it anywhere. All of that happening in a Spark environment, and being able to then, if you want to take actions on the back of that or spill it off into disk for offline analysis at some later stage. And that's not, of course, not the only streaming engine out there. There's lots of them out there on the floor. Probably another very popular one might be Flink from an open source perspective as well. But I think when you look at what's happened with Spark and Hadoop, what we've seen in the last year has been seismic. Real shift from just, should you do this on Hadoop, or should I just load my data on cloud storage and use Spark as a service? And given that all the cloud vendors have put HDFS APIs on top of cloud storage to make it smell like, taste like, look like HDFS, even though it isn't, you can effectively just run Spark as a service. A good example might be Microsoft Azure Databricks running on top of the Azure Data Lake as a good example. But we've also got Hadoop itself as a service on the cloud as well, several vendors listed there. And then we've got relational databases, analytical relational databases. These are databases from the ground up that were relational databases, but they execute SQL queries in parallel. It's not single-threaded SQL queries. The query comes in, it's optimized and run into different, broken up into different parts, and run in different nodes to do massively parallel SQL query processing. Probably pioneered by Teradata as much as nearly 40 years ago now, and is now implemented by a lot of database vendors out there, some of them doing it in memory, MemSQL, some of them doing it in GPUs like Kinesis and BlazingDB, GPU-based databases, some of them more broadly out there, including the new Azure Synopsis Analytics, which Rohan Kumar just announced right on this stage yesterday that Microsoft have launched. And so what we're doing with that is massively parallel query processing. So you can get very, very large relational databases out there into the hundreds of terabytes, in some cases beyond hundreds of terabytes with massively parallel query processing. So for me, it's a complete myth out there that relational databases don't scale. It's how you're using them and what you're using them for, but for data warehousing, this is absolute sweet spot where massively parallel databases have for years been very, very effective. And now we've got vendors releasing databases at the edge, because it's just not going to be practical to bring all that data from all of those devices out there all the way to cloud or all the way to a data center before you can process it and analyze it. I have to do it sooner than that. And so what we're now seeing is, well, if we can't bring the data to where you want to process and analyze it, we've got to go the other way. So we're seeing databases going out there, we're seeing analytics going out there, we're even seeing pipelines to process data and integrate it out there, being pushed all the way out into that landscape beyond cloud. And the question is, do we have to have multiple different tools for edge, other ones for cloud, other ones for data center, or can we move to a kind of common approach to doing this, and it doesn't really matter where you want to deploy this stuff? And I think that's what's kind of going on at the moment. We've ended up with a number of pieces. Now, big enterprises are saying, look, buying all these bits and stitching it all together is kind of challenging. Is there a way in which we could move towards a common approach to doing this and organize teams to be able to handle that? What we are definitely seeing is all of those different workloads all now running in the cloud, but we're also seeing vendors now looking at trying to manage it all from a single console. Whether it's in one cloud or multiple clouds, and again, a good example of that would be what Cloudera showed this morning here on the stage in the first talk this morning, the emergence of CDP, which is not Hadoop. It's a facility to spin up multiple different types of Kubernetes clusters for different use cases, all off of a common place and potentially accessing data on cloud storage. At the moment, it's only on HDFS. I think it's only a matter of time, on AWS. It's only a matter of time before it rolls out on Azure and other examples. So what we're seeing is a whole range of different data stores here. Stuff at the edge, NoSQL databases coming in, particularly being deployed in customer-facing applications to speed up the ability to read and write and give good responses in the front office. But there's some side effects to that, like data quality has kind of deteriorated, I think, a lot because of NoSQL databases, because you don't have a relational database anymore to check integrity of the data. It's up to the programmer whether he or she checks the integrity of the data when they write it into the database. But nevertheless, major adoption and growth in NoSQL databases for operational applications, particularly as they start to introduce ACID properties to guarantee transaction processing. We've seen graph databases. We see Hadoop systems. We're now seeing edge databases. And so the question is, how does it all come together? And I think the first thing has got to be, can you somehow build a setup for your business where data and analytics is at the middle and we can wire it into everything? Because if you listen to, say, Rob Thomas's session this morning, which I thought was very interesting, he talked about AI. He said AI is a complete game changer for all of us. And then the question then becomes not about just building models, it's about using them. And we're not all going to use them in a cloud or just in a data center. We're going to, or just in the edge. I want to build models that are going to be deployed at the edge. I also want to build models that are going to be run in a data center, that are going to be run in a database, that are going to be run in a cloud. I'm going to need all of it. And the question is, for what purpose are we doing these and building these models? If I'm trying to solve a business problem like reducing fraud, I can build real-time streaming analytical models to stop a live transaction in flight before it commits, to detect it as a fraudulent transaction and stop it. That's real-time analytics. But I can also go onto a graph database and load data in there and try and identify a fraud ring. It's still a fraud problem, but it's just a different platform on which we're having to deal or solve with some of those fraud issues. And so it's a collection of things that we're building across this operating environment where we want to deploy things in order to solve big business problems. And it doesn't mean it's all going to happen on just one physical platform. So data architectures really matters if we're going to be able to deliver trust and trusted data and trusted analytics across that operating environment. So the question is, how do you go about doing that? So let's start with the traditional data warehouse architecture, something that's pretty familiar to most of us. This is absolutely been, for a very, very long time, the kind of place where analytical relational databases have lived. Massively parallel databases for staging areas and for your data warehouse itself and for your data marts. You may get OLAP databases, that's cube-oriented databases, something like Microsoft SQL Server Analysis Services or the Oracle Hyperion stuff as an example there. Or it may even be virtual cubes like AtScale or something like that. But the point about this is, it's been very often the case that I load data into staging tables in a data warehouse. And then I run ETL jobs and transform data between staging tables and production. So in this case, the staging and the production tables are both in a relational database. It's very, very common in data warehousing today. It's also very common to see analytical, massively parallel relational databases underpinning data marts. Master data, hardly talked about. Probably the most widely used data in any business. Customers, products, suppliers, materials, assets. Everybody needs master data because we need it in analytical systems and we need it in operational systems. And MDM is becoming important. We've put that primarily on SQL databases. Not necessarily massively parallel SQL databases, but just ordinary relational databases. Similarly also, we would want to synchronize the data coming out of there with both analytical systems to feed it into data warehouse and back into operational systems to make them consistent as well. NoSQL databases, we talked about those. We said operational NoSQL databases and analytical NoSQL databases. And I said analytical would be graph and operational the other types. So here you see the other types as a data source to our analytical environment. So we may be capturing data in this world, and now we're going to take that data and move it into our analytical world. And then I can add graph databases into here and start doing things like maybe bringing in data and using it as a data mart, using graph as a data mart. Or I could introduce graph to accelerate master data management and understand all the relationships across all of those key entities. And I could also build up a graph database that's just pulling data straight in to do some kind of analysis totally independently of any kind of data warehouse, such as a fraud kind of use case or a cybercrime kind of use case. But in that case, they may need massively parallel graph databases, several of which are out there on the floor. For example, I've noticed vendors like TigerGraph, for example. And then I've got to put some kind of data lake in place. Now, there seems to be a myth that a data lake has to be Hadoop. Absolutely not. It could be cloud storage. And that's two examples of a centralized data lake. But I have customers with logical data lakes where they haven't got one data store. They've got multiple data stores dedicated to ingestion. They've got multiple data stores dedicated to curation. And then they've got multiple data stores dedicated to trusted data that they're producing. And so it's a logical data lake consisting of multiple data stores. So it doesn't have to be a centralized data store. You can't ask a company that operates in 100 countries to move all their data to one data store. It's just not practical. So we've got to find a way out of it. But zoning within a data lake, whether it's cloud storage, whether it's Hadoop, or whether it's a logical data lake, is organizing it to be able to understand where the data is and have a catalog to know where all the data is within it. And then we can put data science on top of that. So data scientists are going to access trusted data if we can to speed them up so that they can use Jupyter Notebooks. We can use RStudio or whatever you want on top of something like Spark to scale that. Then about streaming, well, we can do streaming analytics at the edge, or I can push streaming data into Spark, for example, and do it there. And now I'm doing in-flight data. I'm not landing it anywhere. I'm doing in-flight data, analyzing the data, and taking action on the data long before I store it anywhere. And whether you do that with Spark or whether you do it with Flink, the point I'm trying to make here is how does streaming data fit in a data architecture? You can't stuff streaming data into a staging area and go through a batch process of getting it out of there and putting it somewhere else, and getting it out of there and putting it somewhere else, and getting it out of there and then giving it to a user. Because it takes too long. There's too many hops. I have to act on live data in either near real time or true real time. And I can't stick it in a staging area and use a classic data warehouse architecture. But what I might want to do is analyze it and filter out what's interesting. And having already taken action, I might want to filter that data into my data lake and then merge it with other stuff and use it offline, either going into my data warehouse or in further data science projects, building models, and so on. And so be able to handle that. And then I've got too many data marts. I've got lots of customers with too many data marts. It's copies of data. It slows you down. More and more copies all over the place. More and more things to change if something has to change in a warehouse. And so the question is, how do we get agility into data warehousing? Yes, we can use massively parallel SQL databases, but I see new data modeling techniques there, like Data Vault, instead of, say, classic Inman kind of approach. We're seeing the ability to change quickly at the data warehouse, but how do you get more agility in your data marts? We still want star schemas there, we still want Kimball there, but could I not give me virtual data marts? Use data virtualization, get rid of physical data stores. I can now get vendors like TIBCO on the floor here with data virtualization with massively parallel in-memory database inside, with Spark inside it. And so it's data virtualization with Spark inside it. That's out there today. And when we have that kind of capability, and so we have the potential to simplify architecture, getting rid of physical data stores. And so what you're now seeing is we're beginning to use these different kinds of data store in an end-to-end architecture. Whether or not they're in the cloud should make no difference, or whether or not they're physically in a data center should make no difference. But we can link these things together to make them work for our overall enterprise. And then shorten the time to value by, well, even if we do put those data stores in place, how do you get the data flow moving? And it's back to silos again. We can't continue like this because the cost of data integration is too high. If everybody's using their own tools and every silo, we can't share. Because you can't just assume you buy this tool, and that tool, and they just share. Because there's no standard for metadata. The only standard for metadata that's emerging is an open source one. And it's visible here at the show. On the IBM booth, there's a bunch of guys with ODPI Ageria on their back. That's an open source emerging metadata standard. And it's a very interesting one, very young one, only maybe a year old. And it's really gathering momentum fast. You should go talk to those guys. Very, very interesting what's happening. Maybe we might finally get a metadata standard in our industry to share things and understand what exists across multiple tools. I only see one option for that, and that's that Ageria project right now. But for me, the question is, how do you rationalize this thing? How do you if we can use all of these data stores in an architecture, what else do we need to do? Well, we need to come up with a common approach to being able to prepare and integrate data. It shouldn't matter whether it's a user that needs to do it, a business analyst, a data scientist, or an IT professional. Couldn't you have role-based common platform to do that? That's what we call a data fabric, going across multiple kinds of data stores in multiple clouds. And we want to be able to have a catalog to know what's out there. Again, lots of catalog vendors out on the floor over the last 2 days. And this fabric has to go across multiple clouds. It has to go across edge. It has to go across data centers. And we need to discover what data is out there in those data stores. And we need to have multiple people using the different user interfaces of a common fabric to prepare and integrate data for whatever environment it needs to happen in. And the explosion of data fabric vendors in the marketplace is happening at a pace. This year alone, seeing some major new vendors like Amazon enter the game, vendors like Google enter the game. And we need to collect the data from multiple underlying systems and populate the catalog to know what data is out there. And we need to organize our teams on top of this common environment in order to deliver value. And then build ready-made products, ready-made data assets, and publish them in your catalog so that consumers, we can accelerate the last mile and get consumers to drive new value. So shop for data, ready-made. If you could get 60 or 70 or 80% of what you need ready-made and it's trusted and it's got lineage and it's in a catalog, how much time would it save you? So that I can get a curated thing going with a data lake. I can deliver trusted assets that are picked up and give you virtual views of it, and then invite people to come in and consume that data and go drive value with it. It's what I call accelerating the last mile. So that they can pick up, drive value on a trusted base of ready-made assets. And then if they build new assets with those things, then publish those back into the catalog. But as long as you put it through a governance process first, and make sure everything that we're going to publish in this catalog is trusted, it's documented, it's got lineage, etc., so that we can then build up incrementally a completely new set of valuable assets so that the next people who come along find not just 60% of what they need, but 70% or 80%, and so they get faster and faster and faster to deliver. That, for me, is really where we've got to get to here. We're dealing with lots of technology, lots of data stores, but we've got to find a way to be able to put all of these different kinds of data stores together and make them work for us and still deliver value. The expectation is, as the Americans would say, that we can turn on a dime, and everybody's going on about agile. Well, you're not going to get agile unless you can figure out how you can deploy these kind of data stores, put them together, and create a common approach to preparing and integrating data that's shareable and understandable and trusted, and then accelerate the last mile by giving them ready-made rather than asking them all to go back to raw data and give them self-service tools and go, you figure it out. For me, that's the thing that's not going to work. If we just give everybody self-service tools and say, here's the raw data, you figure it out. I wouldn't like to go to lunch and would like to have some chicken and walk in and somebody hand me a raw chicken and some ingredients and say, here you are, you figure it out. I don't want to do that. I want ready-made. And I want to speed up my ability to deliver the value. So I hope that's given you an idea of what you might be able to do with all the technologies on the floor to string them together across a landscape that involves edge, multiple clouds in your data center. And I'd just like to thank you again for the time. Thanks again. Cheers.